A detailed explanation of probability sampling techniques, including definitions, explanations, and examples to support your Chapter 3 methodology thesis writing. Probability sampling is a method of selecting a sample from a population in such a way that every member has a known and equal chance of being included. This approach is fundamental to quantitative research because it supports the generalization of findings to the larger population. In probability sampling, randomness is the core principle, minimizing bias and increasing the study's external validity. There are several types of probability sampling techniques, each suited to specific research objectives and population structures. These techniques include simple random sampling, stratified random sampling, systematic sampling, cluster sampling, and multistage sampling. Let us first explore simple random sampling, the most basic form of probability sampling. In simple random sampling, every individual in the population has an equal chance of being selected. This can be achieved using a random number generator, or drawing lots. For instance, if a researcher wants to select 50 students out of 200 enrolled in a school, they can assign each student a number and randomly select 50 numbers. This method ensures impartiality and is easy to implement when the population is small and homogeneous. However, it becomes cumbersome for large or geographically dispersed populations. Moving on to stratified random sampling, this method involves dividing the population into subgroups, or strata, based on shared characteristics. These strata might include age, gender, grade level, or program type. Once the strata are defined, random samples are drawn from each stratum proportionally or equally. For example, a study on reading habits may divide a population of 1,000 students into strata by grade level. Grade 10, 11, and 12. If each grade has 300, 400, and 300 students respectively, and the total desired sample is 100, the sample could include 30 from grade 10, 40 from grade 11, and 30 from grade 12. Stratified sampling ensures that key subgroups are adequately represented in the sample. This enhances the precision and comparability of results across different categories. Systematic sampling is another widely used technique in educational and organizational research. It involves selecting every KTH individual from a list, where K is the sampling interval. For example, if a list has 500 names and a sample of 50 is required, every 10th person, 550 × 10, on the list is selected after choosing a random starting point between 1 and 10. Systematic sampling is easy to implement and can reduce selection bias. However, if there's a hidden pattern in the list that coincides with the sampling interval, it may introduce bias. Cluster sampling is particularly useful when a population is widely dispersed geographically. In cluster sampling, the researcher divides the population into clusters, usually based on location or institution, and randomly selects entire clusters to include in the sample. For example, a study on school readiness might randomly select 10 out of 50 public elementary schools and include all students from those schools in the sample. This method reduces logistical costs and time associated with data collection. However, it may increase sampling error if clusters are not homogeneous. To address the limitations of cluster sampling, researchers may use multistage sampling, a more complex form. In multistage sampling, the researcher applies multiple levels of sampling techniques. For instance, a researcher may first randomly select schools, cluster sampling, then randomly select teachers within those schools, simple random sampling, and finally survey all students taught by those teachers. Multistage sampling is efficient for large-scale studies where a complete list of the population is unavailable. Now, let us look at examples that show how each technique is used in real studies. Suppose a researcher is studying attitudes toward blended learning among university students. Using simple random sampling, they could obtain a list of all enrolled students and randomly select 200 for the survey. If they want to ensure equal gender representation, they might use stratified random sampling with strata based on gender identity. Systematic sampling might be used by selecting every fifth student from a autre list sorted alphabetically. If the study spans several campuses, Cluster sampling might involve selecting entire classes or campuses at random. For a national study, multistage sampling might involve choosing provinces, then municipalities, then schools, and then students. Each technique offers advantages and challenges. The choice depends on the research goal, available resources, and structure of the target population. In school-based research, simple random sampling is easy when student records are complete and centralized. But when dealing with multiple campuses, cluster or multistage sampling is more practical. Stratified sampling is crucial when comparing differences across subgroups like gender, course, or location. Let's consider a study that investigates stress levels among nurses in a regional hospital. A sampling frame of all nurses can be developed from HR records. If the researcher wants to include equal numbers from each department, stratified sampling would be ideal. Alternatively, if the researcher randomly chooses every fourth name from an ordered list, that's systematic sampling. In health surveys in rural areas, cluster sampling might include selecting barangays randomly, then households within those barangays. If the list of all barangays is too large, multistage sampling becomes efficient. Randomness in selection reduces the risk of selection bias. For example, when studying student discipline records, randomly selecting students avoids overrepresentation of any specific group. Random number tables or software like Excel or SPSS can generate random samples. In stratified sampling, it is important to use proportional allocation unless the research design requires equal representation. In systematic sampling, care must be taken to ensure the list is not ordered in a way that introduces periodic bias. Cluster sampling assumes clusters are representative, which may not always be true. Hence, more clusters with fewer individuals may be preferable to fewer clusters with many individuals. In multistage sampling, complexity increases, but it is efficient for large populations without a single sampling frame. Ethical considerations must be applied in every type of sampling. For example, all selected participants must give informed consent regardless of the sampling method. Reliability of results from probability sampling supports the use of inferential statistics. This allows generalization from the sample to the larger population with measurable confidence. Response rates also affect the effectiveness of probability sampling. High non-response rates may distort the randomness of the original selection. To mitigate this, oversampling or follow-up strategies are sometimes employed. In academic studies, probability sampling increases the credibility and acceptance of findings. For instance, journals and panels often prefer studies with clearly defined probability sampling methods. Sample size determination is also a key part of probability sampling. Tools like G-Power or online calculators help determine appropriate sample sizes based on confidence level, margin of error, and population size. Suppose a researcher wants 95% confidence with a 5% margin of error from a population of 1,000 toddlers. The recommended sample size would be around 278 using a standard calculator. Probability sampling also supports subgroup analyses. For example, stratified samples allow comparison between genders, regions, or age groups. Cluster sampling is often used in educational assessments like PISA or NAEP. These large-scale studies rely on school and classroom clusters to reduce cost. Systematic sampling is common in business research, such as surveying every 10th customer. It is quick and does not require full randomization tools. In policy research, stratified and multistage sampling are common to ensure geographic and demographic representation. Data analysis techniques like weighting may be required in complex sampling designs. These adjustments account for unequal probabilities of selection in stratified or multistage designs. Probability sampling is not always easy to implement, but yields the most generalizable results. The sampling technique must be aligned with research questions, design, and analytical tools. When documenting your Chapter 3, clearly state the type of probability sampling used. Explain how the sampling frame was developed and how randomness was ensured. Provide justification for the chosen method, and describe any steps taken to reduce bias. Include the sample size calculation and any stratification or clustering logic. Describe challenges or limitations in applying the method. For instance, logistical issues might force changes in sample size or selection method. Reflect on how the technique impacts data quality, validity, and generalizability. Probability sampling is often contrasted with non-probability sampling. Be clear why you chose one over the other. In quantitative theses, probability sampling adds rigor and allows for significance testing. Choose simple random sampling when access to a complete population list is available. Use stratified sampling when subgroup comparison is vital. Systematic sampling suits ordered lists or time intervals. Cluster sampling fits large or dispersed populations with group organization. Multistage sampling offers flexibility in hierarchical or multi-tiered populations. Tools and software make implementation easier, but sound design remains essential. Finally, clearly present your sampling strategy in Chapter 3 with tables, figures, or flowcharts if helpful. This ensures transparency, reproducibility, and academic integrity. By thoughtfully applying probability sampling techniques, your thesis gains methodological strength and real-world relevance. If you find this content helpful, subscribe to stay updated on the next tips for writing Chapter 3. Feel free to comment below with topics you'd like us to cover in future content. Thank you.
Coffee cup, minds in a race, staring at the screen, trying to find my place. Outlines messy, deadlines tight, gotta make this thesis shine so bright. Sources, research, writing flow, draft and edit, take it slow. Citations right, no mistakes, one more page, oh for goodness sake. Don't deny it, every word refine, revise it. Step by step, don't lose your mind. That degree's about to shine. Review's long, but I push ahead. Methodologies got me seeing red. Data's done, now analyze. Find the gaps and theorize. Feedback's in, don't be stressed. Rewrite, refine, do your best. Pay visions up, take a breath. This thesis stands the test. Write it, cite it, stay excited. It's only fair. Late night coffee cup, minds in a race, staring at the screen, trying to find my place. Outlines messy, deadlines tight, gotta make this thesis shine so bright. Sources, research, writing flow, draft and edit, take it slow. Citations right, no mistakes, one more page, oh for goodness sake. Write it, cite it, don't deny it, every word refine, revise it. Step by step, don't lose your mind. That degree's about to shine. Lit review's long, but I push ahead. Methodologies got me seeing red. Data's done, now analyze. Find the gaps and theorize. Feedback's in, don't be stressed. Rewrite, refine, do your best. Transitions up, take a breath. This thesis stands the test. Write it, cite it, stay excited. All this work, can't deny it. Step by step, you're almost there. That the thesis life, it's only fair.